Hi folks, welcome to the Webinar Wednesday presentation of the virtual wind tunnel in SOLIDWORKS Flow Simulation. My name is Damon Tordini. I'm a product manager here at Hawkridge Systems, and we're going to be taking a look at the functionality inside SOLIDWORKS Flow Simulation that makes this product a good fit to perform aerodynamic testing or predict the aerodynamic performance of anything from a small scale UAV to a full-scale passenger aircraft or equipment that's mounted on such vehicles and everything in between. If you're designing such a product or vehicle in SOLIDWORKS currently, you probably know that the only real reliable way to physically predict the performance of an aircraft is wind tunnel testing. In most cases, you'll have a scale model of some sort constructed of your vehicle, and that might require either building your own small-scale wind tunnel or renting out time at another facility. And of course, building such prototypes, renting the wind tunnel, and gathering all the data can be expensive. It can be time-consuming. And while wind tunnel testing is always going to be an important part of aircraft design, especially if you're early on in the design process and you've got a lot of design alternatives that you want to try out, for example, different airfoil shapes, maybe fuselage lengths, wingspans, etc., it's not practical or cost-effective to do all of those comparisons physically in a wind tunnel. So a solution, of course, is if you're doing the design of this kind of a vehicle in a CAD program like SOLIDWORKS, you can virtually test a lot of those changes in advance and basically do some trade studies to figure out what design is probably the best or the best option before you go build that prototype and submit it for testing. And hopefully that will help you evaluate a lot more possibilities up front before you then try to nail down the real world performance in the lab. So we're going to look at how quickly you can get that kind of feedback on a SOLIDWORKS model so that as you're making all of the normal design changes that you might try during the modeling process, you can evaluate those changes for aerodynamic performance rather than just making your best guess. So of course, the way that you would go about this after creating some geometry with SOLIDWORKS, or of course, potentially importing a file into SOLIDWORKS, is to use one of the SOLIDWORKS simulation products. And we have both SOLIDWORKS simulation as well as Simulia analysis products here at Hawkridge Systems. And as far as aerodynamic performance goes, the tool that we're going to recommend most of the time is SOLIDWORKS Flow Simulation. It's the built-in CFD or Computational Fluid Dynamics tool for SOLIDWORKS, and it's a great fit for doing aerodynamics, as we're going to talk about in a moment. Some of these types of problems could be done in certain conditions by Simulia Abacus or maybe some of the other Simulia programs or apps out there, but in most cases, there's not a reason to go that route to one of those other programs, unless there is a very specific type of, let's say, multi-physics or more of a structural interest in those kinds of problems. If you're trying to study wing flutter stress inside some components while airflow is passing over them and that kind of thing. But as far as pure aerodynamics goes, SOLIDWORKS Flow Simulation is going to be not only the easiest tool to use, but also probably the most valuable. So in case you're not familiar, flow simulation is the general purpose fluid flow tool for SOLIDWORKS. It can simulate the flow of gases and liquids in or around any solid geometry that you create in SOLIDWORKS. And it does the heat transfer associated with that at the same time. And basically it's set up to be a CFD tool that any design engineer can use. You don't have to have a lot of detailed expertise in using CFD or a lot of knowledge about how to mesh the boundary layer properly or what turbulence parameters to select. So it's a robust tool that can handle a lot of different types of scenarios, a lot of different types of aerodynamic situations, among other things. And it's going to make it possible for pretty much anyone that's doing the design in SOLIDWORKS and has some basic knowledge about what the engineering parameters around the aircraft performance are to run one of these simulations. So this is how we're going to be able to iterate the design quickly while evaluating the aerodynamic performance and not have to export the geometries to some other interface or to do a lot of kind of separate work just to create a model for simulation rather than staying within the SOLIDWORKS environment. So what makes flow simulation a good tool for aerodynamics? Well, first of all, SOLIDWORKS Flow Simulation can compute both laminar and turbulent flow. Of course, turbulence is a huge importance in any aerodynamic application. In most programs at smaller scales, turbulence is not directly modeled, and instead we use what's called a turbulence model to estimate the formulation of turbulence. For example, very small eddies, what the length of those eddies are, and the frequency that they occur at, etc. And so in most of these situations, particularly if you are interested in the kind of large scale aerodynamic performance of the whole craft, flow simulation is more than capable of using the Navier-Stokes equations to calculate all those parameters. And the turbulence model is automatically encoded so that you don't have to manually set it up or specify the parameters you want. Flow simulation can also handle compressible fluids, like any gas is, and that becomes particularly important when you get close to high subsonic or supersonic speeds. Of course, you need to simulate compressible flow to capture shock waves, for example. And so we can handle up to about Mach 5.0, which is pretty typical for any kind of supersonic aerodynamics CFD program. The other key that's helpful here, and one of the main reasons why this is a good tool for aerodynamics, is what we have called solution adaptive meshing. This is one of the core functions of the flow simulation mesher and solver that has been there from the start, which allows the simulation to automatically refine the mesh during the calculation to better capture important aerodynamic effects that maybe you didn't expect. For example, if you look on the bottom right there, that is a supersonic aerodynamics problem where we've got bow shocks coming off that fighter jet, off the aircraft. And of course, if we didn't know in advance where those were going to occur, we would have had to run that simulation with a really fine mesh all over, basically throughout the entire computational domain. Whereas instead, the solution adaptive mesh can see those large pressure gradients developing during the calculation and capture them, basically auto refine itself to capture that better and give you much better downstream results. And so all of this stems from the fact that the code and methodology for flow simulation was actually created for aerodynamics. It specifically was created to simulate nozzle expansion on some rocket boosters. So let's look at a case study and see how we would set up flow simulation to give us some feedback here. This is going to be a small reconnaissance UAV, an unmanned aerial vehicle, otherwise known as a drone. So we've got a lot of drone manufacturers that design in SOLIDWORKS, and of course, that means flow simulation is going to be the most convenient way for them to get some aerodynamic feedback. So we're going to look at how you would do an aerodynamic simulation in FlowSim. And of course, we would be able to do that not just as a steady state simulation where we've got constant airflow, but also as a transient analysis. So that would be useful if we wanted to study something that was changing over time. Maybe, for example, the wind speed picking up. We could simulate an acceleration condition at cruise. Or we could simulate something like changing aerodynamic angles. For example, if you were doing a wind tunnel test, you might try to run a lab test where you change the angle of attack of your aircraft so that you can study how lift and drag are changing as you rotate it through that pitch angle. So we can do the same thing in SOLIDWORKS Flow Simulation by running a transient analysis and changing either the side slip or the angle of attack over time, basically changing the direction of the air coming in. And that way we can get a big suite of results for how the aircraft will perform in a bunch of different conditions with only having to run one simulation. So we won't have to rerun it just because we're changing, for example, the angle of the craft, pitching it up or anything like that. We can do all of this at once. And so because all we really need to do is program in the direction of the airflow, there's not a whole lot that we're going to need to specify for the setup. This is going to be very streamlined and pretty efficient. But let's go ahead and look at what the setup would involve. So I'm going to launch SOLIDWORKS here, and let's start by opening up the model that I need. So this is just, like I said, a small scale unmanned aerial vehicle. It's just a couple feet in wingspan. And basically, all I need to make sure of is that it's solid geometry. That's the only requirement for using SOLIDWORKS Flow Simulation. So I have some surfaces in here, but it's also been knitted into a solid body. So the first step is to turn on the Flow Simulation add-in. So I'm going to click right here on my SOLIDWORKS add-ins tab from the Command Manager. And so that turns on the Flow Simulation add-in, and it gives me access to the tab that I need with all of the typical commands. And basically, I can start a new analysis using the wizard. So if I click here, this is going to walk me through the required steps for setting up a new simulation. You'll notice there's nothing I needed to do to the geometry to run a simulation on this. The only thing that I've got in this particular model are two configurations, one of them with the propeller and one of them without. And I can run analyses on both of them, just depends on if I'm interested in studying the rotation of the propeller or not. In many wind tunnel tests, you probably would remove the propeller as well, just to study the overall aerodynamic performance. So let's start here. I'm just going to give my project a name. Let's call it 65 knots changing angle of attack. And the first thing I can do is just set up my unit system however I want. Let's say SI units or American units. And I can also change or customize the units as I would like to something that makes sense for aerodynamics. For example, velocity, instead of feet per second, I could switch to knots. The next screen is where I set up my analysis type. And this is going to be where I make sure to select an important choice here, which is external or internal. So an internal simulation is where all the fluid flow is going to be inside the geometry that you created, like, for example, a pipe or a manifold or some sort of electronics box. Any kind of aerodynamics problem is usually going to be an external analysis. So we're just going to simulate the airflow around this solid model, and the boundaries of the problem will be sort of automatically defined as this computational domain, which is going to be a sort of a wireframe box. Now, there are some other physics I can turn on. For example, I could turn on heat conduction if I also wanted to study, let's say, skin friction heating on the surfaces of the wing or the nose of the aircraft, if this was traveling at a high enough speed that I had to worry about that. I'm going to ignore heat transfer for now, just to save some CPU time. And I probably don't care about gravity or some of these other effects. But what I do want to study in this case is a time-dependent analysis where I'm rotating that angle of attack. And so all I need to do is put in the amount of time that I want to run the analysis for. And that would be the real-world time, let's say 30 seconds. And then I can choose how often I want to save the results of the analysis. I, for example, put in every second, I would get 30 sets of results, 30 different result plots to look at. You'll also notice I've got a rotation option there. That's what I would enable if I wanted to simulate the propeller spinning and, of course, adding thrust and probably changing the aerodynamic parameters near the rear of the aircraft where those elevators are and the vertical stabilizer. So we'll click next, and then at this next screen, we're going to pick our fluid. Of course, Flow Simulation has a pretty big library of fluid because it's used in all kinds of industries, but for aerodynamics, it's probably going to always be air. So we can select air right there, and you'll notice that if I go into the library and take a look at the definition of air, the properties such as the dynamic viscosity and the specific heat, they're defined with temperature-dependent curves. And that's important because if you were trying to simulate an aircraft at high altitude, for example, you would put in the appropriate temperature and pressure at that altitude, and the properties of air would change as they should. So there's no need to create a different version of air just because you're, for example, at 30,000 feet. So we'll just make sure to double-click air. That's added into our project. You can see down here that we were already selected on laminar and turbulent. So the turbulence model is going to be programmed in automatically and will predict where
turbulent boundary layer has formed and where wing separation is occurring. And there's also that high Mach number flow option, which you would turn on if we were above Mach 3. And that would change the solver parameters slightly to a smaller time step, which would help capture supersonic shock waves. For right now, though, we're going to be subsonic, so we don't need to check that box. Now we can also put in some wall conditions. We're going to assume that the surfaces of our aircraft are perfectly smooth, but if I wanted to assume that they had a particular surface finish on there and that there was more surface roughness, we could put in the average height of those rough features, and that would change the boundary layer formation, and it would also affect the skin friction heating if we were including that effect. Finally, at the last tab, this is where we're going to put in the ambient conditions for the craft. So you can see right there, we've got pressure and temperature, and those are going to be the values for just sea level atmospheric pressure and standard temperature in a lab environment. So we'll go ahead and leave those in. We're just going to assume that this drone is, flying at a low altitude, near the coast. But of course, you could change those parameters to anything you want. And then below that, under velocity parameters, that's the key where we're going to set up the actual aerodynamic function of the analysis. And so you can put the velocity in with X, Y, and Z vectors. But what's even better is if you're doing an aerodynamics problem like we are here, you can set this to aerodynamic angles. And instead, what this lets us do is define our longitudinal plane and axis. In this case, that would be the YZ plane. And our longitudinal axis would be the Z axis. And the benefit here is that now I can simply put in my velocity, let's say 65 knots, like that. Or in this case, actually negative 65. And without having to put in any kind of vector components or do any trigonometry, I can change the angle of that free stream flow simply by changing the angle of attack or angle of side slope values right there. So for example, I'm in radians right now, or if I went back to my units here, I could switch that to degrees, which is under the geometrical tab here. We'll go to degrees. And then I could simply change my angle of attack by putting in one number right there, let's say 2 degrees. And you can see that that arrow has shifted direction slightly, and now our aircraft would be pitched up relative to the free stream velocity. So this is how we're going to be able to easily set up a transient simulation where that angle of attack changes over time. And it's the same as us pitching the aircraft up or down. So this is where we would type in a value if we want it to be constant, or if we wanted that to change over time, we could use this dependency option. And we could either punch in a function, a formula definition, or we could simply put in a table. So for example, here, if I'm running my simulation for 30 seconds, I could say that at 0 seconds, I may want my angle of attack to be, let's say, negative 6 degrees. And then at 30 seconds, I could make it maybe positive 12 degrees. And if I see the little preview chart here, you'll notice that that now has given me a changing angle of attack where I'll pitch from negative 6 degrees all the way up through perfectly horizontal at about 10 seconds to a pitch up of about 12 degrees. So I'm going to be able to evaluate all these different positions in the same simulation. And I could do the same thing with angle of side slip as well. So that's all set up. And now what I'm left with is my project tree over here and this rectangular box, which is the computational domain. So everything inside that wireframe box that you see on the screen is where the airflow will be simulated. And in many cases, that wireframe box is bigger than it needs to be. The simulation sets it up very large by default, just as a conservative guess. But you can shorten or shrink that box if you want to speed up your calculation. So for example, I know that I probably don't care about the results off to the side of the aircraft very much, or down beneath the aircraft, so I can simply drag these arrows to reduce that. I can also manually plug in the dimensions of this box if I right-click Computational Domain and go to Edit Definition. So for example, maybe I want to make sure that the front is closer to the craft. but I want the back to be lengthened pretty far so that I can see the wake air coming off of the aircraft accurately. There is another important change that I can make here to the computational domain, which will speed up my simulation even more, and that is to set up the symmetry condition. And as you can probably tell, my aircraft is symmetric, just like most of them are. And so what I can do is make my simulation split through the middle of the aircraft vertically. And then I can set the symmetry condition at that boundary so that I only have to run the analysis on half the geometry, which should run in about half the time. So in that case, the direction here is the x-axis, and I can make my x minimum value 0, which goes right through the middle of the aircraft. And then I simply change this condition here from the normal boundary condition, which would be like an open window basically with the air coming in at whatever speed I picked. I can change that to symmetry, and you'll see this kind of wireframe box appear, which tells you that you're basically mimicking the other half of the simulation on the opposite side of the aircraft. So I can click OK. Now my computational domain is set up, and the airflow is still programmed in from my general settings in the wizard that I plugged in, which again is going to be changing angle over time as we run the simulation. Other than that, there aren't really many other boundary conditions that I usually would need for an aerodynamics problem. Of course, you could put in things like heat sources or even porous materials if you had some sort of a filter. And that would probably make sense more for things like an electronics box that's mounted to your aircraft or any other radar or, let's say, sensor equipment. But for the aircraft itself, the wind speed is probably the only parameter we really need. And so at this point, we can set up the goals that we're interested in and then run the simulation. And so if you're not familiar, the goals are not conditions for the simulation, but instead are like sensors. They help you measure whatever result you're most interested in about the analysis. And that's going to be key for an aerodynamics problem because we'll probably want to see things like drag or lift forces. And so it's easy to set those up with this drop-down menu here and create, for example, a global goal. If we wanted to measure the drag force on the aircraft, all we need to do is scroll down and find the force option. In this case, it would be the force in the z direction would be drag. And because this is a global goal, that means it's simply going to measure all the surfaces of the aircraft. Same thing for the lift. That would be the force in the y direction. So I could check that too. If I wanted to measure, for example, the average pressure on the front of the aircraft, I could do, let's say, a surface goal on one of the faces, for example, the nose, and I could select the average box for total pressure. That's the wrong one there. Let's select that face over there. And then I could also select things like global turbulence goals, or I could try to create an equation goal to measure Reynolds number. Now, equation goals are basically like Excel functions that you can program in that let you set up an equation based on other goal properties you've already created. So that way you don't have to create a separate Excel spreadsheet doing additional math operations. So for example, if I wanted to measure the L/D of my aircraft, that would simply be the lift divided by the drag. So I could click my lift goal, type in the divided by symbol, and click the drag goal. And that'll be measured as such. And I could use that same process to create goals for almost any kind of parameter that I would want. So for example, if I switch over to the one that we've run over here, I've got an equation plugged in for drag coefficient, which is based on some other properties like the average density of the fluid and also the drag force. And in other cases, you might need things like the dynamic viscosity or any other parameter. And those can all be accessed from either the goals or in some cases also the setup conditions in your study. For example, the lift here, you can see is not actually just the lift force, but it's going to be based on that angle of attack that I'm changing. So I've got some terms added in here for what the current angle of attack is. So that way I'm always measuring the lift perpendicular to the longitudinal axis of the craft and not just the global coordinate system. And this is the type of thing, of course, that Hawker Systems can help you guys figure out during some mentoring time, looking at one of your applications one-on-one. So at this point, we could go and check our mesh settings. In this case, we will probably want to leave the mesh at sort of the default size here, level 3. You might want to make that larger or smaller. And one thing that's often popular for aerodynamics problems like this is to increase the ratio factor. For example, I could bump this up to level 2, and that helps refine the mesh more near the surfaces of the aircraft, but not so much further away where my results aren't as important. So that's a popular addition that was added in SOLIDWORKS Flow Simulation 2016. You can also do things like put in the minimum gap size if you have gaps between control surfaces or any external components on the aircraft. So let's go ahead and run this really quick just to see what the solver looks like. This is going to create the mesh and then begin the computation right away. This is going to solve locally on my machine here using all the available CPU cores. Although, as you may be aware, you can send any flow simulation calculation to another machine that's located elsewhere on the network. That just requires you to have SOLIDWORKS installed on that computer with flow simulation, but it doesn't need its own license. You simply load the software and don't activate it. So we'll hit run. This is going to pop up the solver window. It's going to capture the geometry of the aircraft as I've modeled it and then start running the simulation. And in this case, because this is a transient simulation where the angle of attack is changing over time, you'll probably see the results change over time too. You can see right here, I'm getting a preview of what some of these results are. And I could also, if I wanted to, set up a visual cut plot preview as well. And again, because this is a transient simulation, what you'll start to see is some of these values like the force and drag slowly shifting as the angle of attack changes. So this would take some time to run. I can go ahead and stop this. And let's switch over to the finished version. So here's the one I've run already. I can load up my results. And in this particular case, I actually ran the simulation for 60 seconds, for 1 minute, which took on my computer about, it looks like 7 or 8 minutes to run fully. And this is at a relatively coarse mesh. And so now what I can do, first of all, is immediately go look at all the values of these goals. So I can create a goal plot here, or look at the one that I already made, and that just asks me to check the goals that I already measured. I can hit show, and the first thing that this is going to look at is the final value of the goal. So this is going to show me what the lift and drag forces were at the end of the simulation. So for example, this would be where the aircraft is pitched up at the maximum angle of attack. And you can see my lift is about 28 pounds there. My drag is about 5 or 6 pounds. And I've got my L over D and other things like drag coefficient. But what's interesting is in flow simulation, you can not only see the final value of these goals, which hopefully help you evaluate if your product is a kind of pass-fail or if it's the best option, but you can also look at the history of those goals. How did you end up at those values? And for a transient simulation like this one, what you're actually seeing is how those properties changed over time. So you can see right there, for example, at the time of 0 seconds, which is when my aircraft started kind of pitched down, my lift was almost 0, it was barely anything. And then of course, as I started to level my aircraft out and then pitch it up, the lift increases as well. Now also the drag increases, which means the L over D ratio started to go up and then reduce a bit. And then also I can see my drag coefficient going up. So if you were trying to figure out, for example, not just how your aircraft performed at level flight, but maybe what the ideal angle of attack was to get you the best lift to drag ratio, you've just been able to find that by running this transient simulation. Then of course we can go look at all the visual plots to help us see in more detail, why we're getting these results or how we might want to change our design. For example, we could look at a cut plot, and this is basically like a section view where we can see the results on a plane. In this case, I'm just looking at the mesh so far. You can see that it did a fair amount of refinement at the surfaces of the aircraft, which is usually important. But then I could also look at things like, for example, the pressure on the top and bottom of the wing. And as you would expect, we've got a higher pressure on the bottom of the wing where the air is at a lower velocity and a lower pressure on the top. Of course, that's the Bernoulli principle, which is what creates lift and allows our aircraft to fly. We can look at all sorts of things in these plots, like, of course, the mesh or maybe the vectors of the flow. And some of these properties will be more interesting maybe from a side view. We could turn on things like the streamlines, which are dynamically drawn when we zoom in and out on the screen and help us see things like recirculation or eddies or vortices. So again, this is at the end of my simulation here where my aircraft has been pitched up 10 degrees or so. So here's the free stream velocity coming in. And of course, again, there's the flow separating. And if I were to drag this back and forth, I can see that over other areas of the model, like, for example, the wing. I also might want to look at things like a pressure distribution on the surfaces of the craft, which you can do with the surface plot. This just allows us to select all the faces and then plot pressure. And here we're looking at relative pressure, which is basically gauge pressure, right? So what it would read on a normal barometer. And again, of course, you see the high pressure region there at the leading edge of the aircraft, and then lower pressure on the top as the air picks up speed going around the airfoil. And of course, everyone's favorite is to look at the three-dimensional flow trajectories. We can create these flow trajectories by either clicking on faces or edges of the geometry, or by drawing a sketch out in front and selecting that sketch as our starting point. And that will create a number of points in space and then draw the 3D streamlines where the air would go from those points. And we could do that with simple lines or oval shapes or whatever geometry you want. And of course, once we get some of these parameters, the key is going to be evaluating some sort of a design change and trying to figure out which one is better. So in this case, what I did is I made another variation of my aircraft where I shortened the wing. And then I was able to simply clone my project to that new configuration and then hit run. So there's no requirement of redoing the setup or recreating the analysis. And if I run both of these and have two sets of results to look at, I can compare them side by side with the compare results tool. So this is particularly useful because I'll be able to grab, for example, the cut plot and also my goals. And I'll be able to look at those side by side and evaluate not just the pressure contours, but things like the history of goals. And if I just click compare, that loads up the results I need. Let's look at the 65 knots no prop versus the 65 knots shortened no prop. So right away, we can tell that there is a slight difference in the velocity profile from the side of the aircraft. And then if we go to our goal plots, we can see that not only are the parameters at the final angle of attack different, but if we switch to that history view, we can view both curves side by side. So again, without having to build any prototype or reserve any lab time, I'm already seeing the same type of data I would get from, let's say, LabVIEW or whatever monitoring software I use. And I know the effect of a wingspan change as far as drag coefficient, drag, L over D ratio, lift, all these other parameters, so that I can evaluate a bunch of variations up front before I have to actually prototype anything or build any real geometry. So again, you would know that, for example, the longer wingspan gives you more lift. but it also gives you more drag, and maybe you would find what that sweet spot is between the two. So of course, being able to evaluate these kinds of changes quickly is the whole point of SOLIDWORKS Flow Simulation. Being able to compare a design change or even a large suite of design changes, if you were going to do a parametric study, for example, which lets you run a batch of simulations with a bunch of variations. For example, I could try maybe 10 different lengths of that wingspan, or I could try changing the chord of the airfoil at different points. And I can also get a lot of powerful result visualization tools, either what we just saw in the software itself, or creating animations which could be exported for viewing later, either to like a video file or just some images. Those can of course be put on the website or used for marketing purposes. And again, any kind of comparison that we generated that really drives home what the trade-offs of any design change are, they can be exported out to Excel and manipulated however you might want, and can serve as a good indication of why a particular design choice was justified earlier in the software, or earlier when you were using the software for design. And of course, aerodynamics can be done on a variety of industries and products, not just a drone. We've got a lot of companies using this for ground vehicles, for public transportation, even hydrodynamics. If you're doing, for example, a submersible or some kind of, let's say, underwater robotic vehicle. And it's also used in a lot of industries for external aerodynamics of components that go on vehicles. For example, radomes, landing gear, sensors, antenna, almost anything that has some sort of aerodynamic impact that needs to be evaluated. And if you're not familiar, you can even take the results from SOLIDWORKS Flow Simulation, specifically the pressure results from that airflow, and those can be directly exported to the stress analysis in SOLIDWORKS Simulation or other programs, so that you can get an accurate stress simulation of the real pressure contours and not just assuming some kind of uniform load. So some of these features are why we've got a lot of customers using SOLIDWORKS Flow Simulation. You may have heard of Center Rock, which was more of a downhole tool drilling company, as well as a lot of electronics, thermal enclosures, and particularly small-scale UAV companies. And again, it's largely because of the fact that you can do this quick analysis process like we just saw without having to modify or create a special version of your SOLIDWORKS geometry. And you can get almost instant feedback about what each of these changes will do to the aerodynamic performance that you're looking for. And of course, we've got a lot of education pathways for you on this software. We offer training at Hawk Ridge Systems on Flow Simulation, which is a one-day class. We also offer it online. And we can also help you out with a variety of services, everything from just simple one-on-one mentoring, where we could spend some time looking at your specific application and maybe what the best way to set up the problem is, and also how to interpret the results properly, all the way to doing analysis consulting. If you are low on resources and you don't have the time to run something on your own, you can contract us and we'd be happy to do it for you. And if you're not aware, anytime you contract with us to spend some services dollars, we give you a partial credit back towards the purchase of any SOLIDWORKS simulation licenses. So it's a nice kind of benefit of staying within the Hawk Ridge family. With that, I thank you for joining us, and we're going to leave it open to any questions here, if there are any. Otherwise, feel free to send me an email after the presentation. My name's Damon T at hawkridgesys.com. As always, you can contact your account manager or Hawk Ridge Systems support if you have any questions about either using SOLIDWORKS Flow Simulation or any other tools you may already own. And we're happy to discuss if your application is a good fit for this software. Thanks again for joining.